I'm guessing under 2 hours, but yeah. Why is it? Why is it not? Okay, now it's giving me.
It started. It says end stream audio.
No, like, but it's still like.
It started.
Okay, now it's fine. Yeah, yeah. Just want to see this. What is going to do? I said no, record. Once. No, it's just see once. I mean, it's still kind of bad, but I mean, I can't do much other than that. You started?
Yeah.
Should I use a mic or use a mic? Cool. Yeah, yeah, sure. I guess I'll start now.
Just say hello loudly.
Hello?
Okay, 30 seconds.
Yeah, I mean, you can.
Yeah, even without mic also it's fine.
Yeah, I guess I'll just use it.
It's not.
Yeah, I know. I didn't. No, I just looked at his slides and waited. Like, I didn't copy his slides. I mean, I didn't take his slides. Yeah, I think we should just use the exact same term for everything. Exact same term. Yeah, like proper, official. Yeah. No, I mean, I got like some. Okay. Okay, I need to move. Does it look fine, guys? It's fine. Just see how much delay is it. 2, 3. Yeah.
It did come. It did come.
Okay, okay, cool.
No, but it's not visible.
Okay. No, I'll just do this one.
This is very bad.
Yeah, quality is bad, but latency is fine.
I think you could just.
You don't write, so why would I write? Nah.
You have US citizenship on your resume.
Obviously.
Huh?
Because a lot of the US companies they just reject people with that, right? So it takes about a second to like load in, right?
That is fine.
Yeah. Yeah. I think that's fine. Yeah. Are we waiting for anyone else, or should we get started? What do you think? Get started. Cool. Okay. I hope you guys can hear me. Is it coming out of the mic or no? Should I hold it in my hand? Hello? Hello? I hope this is fine. Yeah, it should be fine, yeah. So let's get started. So right now we're going to be covering persistent data structures. I'm hoping you all know segment trees because the entire video is going to be based on segment trees. So if you don't know segment trees, it's probably the best week for you to be in. So yeah, let's get started. Of course, credit goes to Tanuj Khattar again, and SecondThread as well, because I learned a bit of persistence from the tutorial. And we'll be covering these topics. We'll be going over what is persistence, how do you implement it, and the code for it. Then we'll go over a classic problem that's covered in segment trees, which is like finding out the number of distinct values in a range. And we'll show that persistence can solve that problem in online as well. Now, then after that, we'll go over solving the problem of finding the kth minimum in a range and how we can do that online. And there are other miscellaneous techniques that often branch off from persistent segment trees, like dynamic segment trees, and some techniques which we can combined like with hashing to solve like other types of problems as well. So what is persistence? So if we have like 7 tree and we're just trying to find the sum of like random ranges, and we make updates to that, we might want to have access to each and every version of that 7 tree. So if we have a 7 tree that is, let's say, we have an array like this, and so it's 4, 5, 10, 2, 3. We might want to have a 2nd tree on this, and then we make one update in which we update the 10th, like the 10th value to say 6. So we might want a 2nd tree in which that value is 6. And we might want to solve this online. Like we randomly want to find like the second version's L to R sum, all that stuff. So that is mainly supported by precision. Like having access to all versions of your data structure and being able to query it in a pretty fast way. So of course, like if you want to solve this problem, one way is just having q plus one copies of each 2nd tree. And of course, that won't be very efficient, especially if you're working with like very large numbers. So if n is like 25, then this is obviously not going to be like the most efficient way to do it. So what we try to look in persistent data structures is we look at the things that are updated when we go from one version of the 2nd tree to the other, and try to just store those different, like the difference between them like efficiently. So if you look in the 2nd tree, when we make an update to say this node over here, the number of nodes that are actually updated when you go from the version before this and say when the 5 becomes 6, there are not going to be a lot of nodes that are different. All of these nodes are going to be the same. This node, this node, this node, this node, all of these are going to be the same. So there's no point of keeping an extra copy of that. So again, when we update this to 6, the nodes that are updated are this, 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 and this. So what we try to do in making a persistent 2nd tree is that when we make an update to like the bottommost node, we try to efficiently store the new version of it, which just takes about log n more memory, because in a 2nd tree, when we update like an exact point, we're only going to be updating log n nodes. So yeah, like I said, normally nodes that are updated each update, and instead of storing a copy of a 2nd tree for every version we need access to, we can just keep track of the nodes that are updated. And of course, this is how you would normally write an update, right? You just find the node, like the position that you need to update, you set the value, and then you just iterate through the nodes and update all the nodes. So again, it's very clear to see that it's login. So one of the best ways to implement persistence in 2nd trees is fat swapping. There is another way called fat node, but again, it's not the most efficient, and I won't be going over it because it's not very useful. But yeah, I'll just go over this. So like I said, we only create copies of nodes that are updated and have them point to the appropriate nodes. So if you look at this, uh, in say node 8, when we update 5, like the value 5 to 6, 8 doesn't need to do anything different. It needs to just remain the same and store the same sum and point to the same nodes because none of them are updated. But if you look at, say, node 4, we're going to want to make a new copy of this node, like just pointing it over here, and it just points to 6 and it updates its value. So we went from 5 to 6. So this, we should make a new node. Okay, this is getting a bit ugly. One second, I'll just clear this up. Yeah. So we're looking at this node and we update it to 6. So the way to make new versions of the node, like what we want to achieve is we make a new node over here, a new node over here. This one has 6. We have a new node that points to this new 6, and it points to the original -1 because we didn't have to make any update to that. So this will now store 5. And again, we have to update 20 as well, so we make a new copy of it and make this 21, and it points to this, and it points to the original node 16 because again there are no updates to it, and make a new 29 node, and instead make it 30, which points to this and this. So this is essentially what we want to achieve. When we're updating the nodes from bottom to top, we want to make sure that we update the pointers of that new node to the respective new nodes that we just created. And for the rest of the things, you can just keep it as it is. So yeah, back to back path swapping precisions. Only login nodes are created per update, hence updating precision second trees is login as well. And querying a specific version is just starting your query on the appropriate root version. So say like we have this segment tree and we have second, we have two root nodes now, right? So say that we want to query the original segment tree. We just need to start at this root node and go to the appropriate pointers. Yeah. It does, but it's not doing it properly. Yeah, yeah. So if we want to query like the original segment tree, we need to start off with this root node and then just perform the query. And you would know like which node you need to go if you want to go to the left, you want to go to the right, all of that stuff. And if you want to query the new one, you could just query this new node that you just created. And again, their pointers are also updated. So if you want to make a query, say this to this range, you just go along these pointers and query whatever ranges you need. And again, like it'll just execute properly. So yeah, you can see it here as well. When we update this node 1 to 3, it ends up creating these new nodes. And if you want to query the old version, you can query this one. Otherwise, you can query this one. So again, like this feels like very abstract, and you don't exactly know how to implement this because you'd feel like it's like very ugly. You have to deal with pointers and everything. But again, all thanks to Tanuj Khattar, like he has a very clean implementation of this. And I'll just go over this implementation so that you guys can clearly understand how exactly this works and how it's actually of the same time complexity as a normal segment tree. So what we have in this is we have three arrays, L, R, and ST. So what these arrays are used for is that, again, ST is just your normal segment tree node in which you just store the value that you have. So ST would just store these values, right? And L and R are basically the node which is your left child and which is your right child. So if you had an index for all of these, so say this was 0, this is 1, 2, 3, 4, 5, 6, 7, 8, 9. So L of 0 would basically say that, okay, it's equal to 1 because the left child of 0 is 1. The R of 0 is 2. And say something like L of 8. So L of 8 is 5 and R of 8 is 9. So like if you look at a normal segment tree, like if you want to query your left child and your right child, and you know that your node ID is like pos, then you know that your left child would be 2 into pos, and your right child would be 2 into pos plus 1. But again, we don't have that luxury of just indexing it like directly like that. We need to have another level of indirection too, because we need to support updating nodes, and it gets very messy. So instead, we just have like a bit of an implicit pointer, which just says that okay, the left child index is going to be like 5 or 9. So that's the reason why we have these two vector arrays. And so I hope that's clear. Now we'll just go over the update function. So we have a lot of parameters. So pos is just the place that you want to update. So if you just go back to this, you want to update 10. So we basically say that okay, we want to update position 3 with value 6, something like that. So am I going to fast? How does compare to? Oh, it's just that you have to create dynamically. Oh, bump allocator. Oh, then it's not that much different. I mean, I see. The thing is, okay, I'll just explain this. Yeah. So another reason why you would prefer, what do you say, using arrays instead of actual pointers is that uh, there are a lot of nodes that are not created at the start, right? So all of them are just going to be initialized to zero. So in a persistent segment tree, it's a lot more implicit that it just like happens off. So st0. Okay, no, wait, I'll go over this later. But basically, is I'll just go over this later. But the main issue with having pointers is that you have to deal with when the pointer points towards null, and another special case that you have to include in your implementation. If you just do it this way, it's a lot more clear, and you can handle that case a lot more like simply. So yeah, I'll just go over the rest of the implementation. So yeah, so in update, know that we're actually returning an integer. So what we want our function to do is that it's going to take in the parameters that we want. That okay, we want to update this value, and the node that we're currently at covers this and this range. And what we want update to do is that if that node creates a new copy of itself. So if you're over here, and we realize that we need to make a new copy, so we make a new copy here. Uh, what int update will do is that it will return the index of the new uh, segment tree node that we just created. So if you're here, you know that you're at 2, and then you realize that you need to update 3. So you end up creating a new copy of yourself, and you say that, okay, cool, I'm getting index 8. So in that case, you basically like the update function for this will return 8 so that the node right above it will know which node to point to after the entire like recursive call is done. So yeah, we have pos, L, R, val, ID. So again, pos is the index that we want to update. L and R are the ranges of the node. Val is the value that we want to update the array pos at, and ID is the current ID of the node that we're at. So we'll just go over the implementation. So the first line is basically just saying that if you're out of range, like if the node that we're currently at is out of range for pos, then there's no requirement for updating it. So we can just return on you the same ID that we had because there's no copy, there's no node copying that we do in this entire subtree. Otherwise, we're essentially saying that, okay, cool, this this node is like an ancestor of the node that we're updating. So we need to end up creating a new copy of it because everything along that path has to be updated. So we say ID is equal to plus plus node ID, which is essentially just saying you're getting the next index that's available. And yeah, we just calculate mid. So one special case that we have handled in persistent segment trees is when we reach like the final node. So if L is equal to R. So again, that's I'll just show you some of this ones. Yeah, I can't hear you. L and R. Okay, cool. I'll do that. I'll just cover this part. Yeah. Where was I? Yeah. Okay. Wait, the big L, big R, or like the parameters L and R? The parameter. Yeah. So in the update function, the L and R basically correspond to the node, the range of the node. So again, if you look at, cool. I'll just make this array. So if we have this array and we just index it by 1, 2, 3, 4, like we have this array, right? So this node would basically correspond to the range 1, 1. This would correspond to 2, 2, etc. Right? And the range that this node corresponds to is 1, 2. This one corresponds to 1, 4, etc. So yeah, the range of the current node. That's basically what it signifies. Yeah, yeah. We're right now just dealing with point updates. Yeah, so pos is the point that we're updating right now. And LNR is the range of the node that it covers, of the original array. Yeah. So yeah, like I was saying, if L is equal to R, return this. So this happens when again we're at the position that we wanted to update. So if you look at this example, uh, we want to update 1 to 3. So this value. So once we reach this value, once we reach this value, uh, all we need to do is just make that update. So if you look at the original segment tree update as well, you go directly to the point, to that point where you need to update the value. So I'll just, sorry, go back here. Yes, so if you look at like, try and make an equivalence, this is what we're essentially doing at that if condition. We're just setting that value to what it's supposed to be. So, and once we do that, we just go back up and update the nodes respectively, right? Like every single parent of it. So, just like just like that, when we're at L is equal to R, we just set that value to what we want it to be, and return the new ID. So, again, uh, you guys might not know this, but if we're doing something like this, return something here and X. In C++, it's just going to return X. So you can just combine some statement and then return a new value after that. So yeah, what we're doing here is that we're making a new node again, which is of the index ID. We're sending it to val and returning the new node's ID. So I hope that's clear. And now what we're going to do is basically, if it's not L is equal to R, then it's basically going to be a parent of the child that a parent of the node that we just updated. So we go into LID, in which, so if you're over here, uh, we know that, yeah, this just got updated to node 3. So, okay, cool. I'll just write this down actually. I'll just, yeah. So, we have this call at pos3 we want to update, yeah, at pos4 we want to update let me see, of this and just say 0, 1, 2, 3, 4, 5, 6. So currently this is like all of the nodes that have been initialized, and we don't have version yet, and we're trying to create version 1 after updating position 4 from 1 to 3. So this recursive call is going to go all the way till we have this recursive call, right? So if we just look at this, L is equal to R, so we're going to have ID equal to 7. So we say that we create a new node of index 7 and say that st ID, okay, wait, I'll just write this here. st ID is equal to 3, and this will return the value 7 because we want to return the ID of the new node. So once this recursive call is finished, you come here, in which the recursive call is update 4, and this covers 3, 4, 3. Okay, no, wait, not. Yeah. 2. Yeah. So once you're finished with this node, we go back up here, right? Because the recursive call was made in this direction. So, yeah, so now we're at 6. No, sorry, we're at 2. And we see that the value returned by our right node is now 7 and not 6. So we need to update our ID appropriately. So it ends up becoming 6. And that happens over here. So in, again, LID, there is no update because the range is actually out of bounds. But if you look at RID, which is the call that we just made over here, it ends up returning a new ID. So we update the pointer of RID to the new node that we have. And the same thing happens when you reach somewhere here, where we see that, okay, this node has been updated, so we update his RID as well. And we create a new node for that too. So it's, I know, a little bit confusing because we're just starting off with the implementation, but I hope that's clear. Uh, any doubts? Any doubts? Cool. If you guys have any doubts, you can just stop me. I can go a bit slower if you want. Sure. Cool. So yeah, and of course, I mean, you do the segment tree node update over here, where you just look at your left child, look at your right child, uh, perform the merge, and then you just return your own ID. So I hope that's clear. So that. Sorry. What? Uh, node ID. Once again, N or node ID? Yeah. Yeah, it's not. It's. I mean, it's just for what do you say? How do I explain this? Yeah. 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 N is not exactly the size of the array. It's just the like. It's Yeah. So, okay, n is basically technically the number of queries that you're going to make, or like the number of updates you're going to do. So, okay, I'll just go over this as well. So, the reason I've allotted n log in memory is, like, I'll just explain that. So, in each update, we're going to be updating at max login nodes, right? And say we're making about 5v5 queries. In that case, every update that we make, we're going to need, uh, again, every update, we're going to need about 18, because we're assuming that our segment tree is of height 18, and we're going to be making around 5 queries. So to support all of those 5v5 into 18 nodes, we're going to need n log n space. Yeah, so the thing is, we don't actually have the original segment tree. So we create it on the fly. Yeah. Yeah. Yeah, so if you look at just making the original segment tree, so you're basically talking about this. Like, yeah. So you're basically saying, uh, like, why haven't we like set aside special memory for this? So the thing is that a lot of the times when you create a persistent segment tree, initially you just assume that your segment tree is empty, and you make these updates like one by one. So again, not the most efficient way, but like you will just ignore it. So if you wanted to create the segment tree, first you put in 7, saying that you want to have 7 at position 1, and it'll create these nodes, and it'll assume that all of these nodes are empty. Yeah, yes, performing n updates. Yeah, that's how most of the people do it. Technically, you can uh, create a segment tree and then, like, in a faster way, and then do it, but most people just do it like this way. And yeah, like, since I was mentioning this, do note that a lot of the times, like, when you're creating a segment tree, these are going to be empty, right? Like, if you if you put this value in, you're going to have 7. Like, these are the values, 7, 7. So you might think that, okay, but when I'm over here, I don't know what my RID is. RID is just going to point to 0 by default, right? So what you do is that you essentially have like an identity node that everyone points to, and everyone just shares that at the start. And this will just, like, if you're doing sum, this will just be 0. If you're doing min, it'll just be 29 or something like that. So that's like one of the good things about implementing it in this way, in which you just need to have one node, and you don't need to like initialize every node to that special pointer. You can just, everyone's just going to point to 0, and you can just have your identity element there. So that's like one of the benefits of this implementation. Yeah, I'll cover that later. Yeah. So I'll be going over performing the queries now. And performing the queries is pretty straightforward. It's almost the same as a normal segment tree. You're going to have your query L, your query R, which is the thing you're actually querying, and L and R correspond to the range of the node that it covers. So similar to the update. And ID is basically the segment tree node that you're at. So if you wanted to query, say, I wanted to query the new versions uh, three, 2 to 4. So what you would do is that you would start over here and say that, okay, cool, the range is 1 to 4. I need to go into this range, which is uh, yeah, 3 to 4, and you just stop here. Over this guy, you go to your left node. You're here. This covers 1 to 2. You're like, okay, cool. I need to go into my right child. You query this, and it's just like the normal segment tree. So all you need to do when you're querying is you supply the original root. You want to supply the root node that you want. Like if you want the first version, if you want the 0th version, if you want any other version, you just supply the appropriate root node, and you just do it like a normal segment tree. If it's out of range, then you just return the identity element. If your node is entirely in range, then uh, you just add the segment tree node, which is HDIE. Otherwise, you just break it down and you descend into your left child and your right child, in which you just say, like, okay, cool. My query is going to remain the same, QL, QR, and the left node is going to be LM range, and you want to go into LID, which is basically your left child, and the same thing for your right child. Yep. Yeah. So I hope that's clear. Any doubts? Cool. So yeah, performing queries is pretty simple, and after a while, like implementing the update function is also pretty simple. But I mean, now that we have this, we'll just not go over the details of the implementation of persistent segment tree. We'll just be looking at how we use the segment tree. So this is just one example. So again, we were going after like how do you find the sum of A of LR after the Vth update. So this is just like some sample code. N is the size of the array, V is the number of updates, and Q is the number of queries. So we have the array, we just taken the input, and now roots v plus 1 is basically going to say, yeah, roots. 1 second. Roots I will basically store the node, which is a version of like the segment tree after the ith update. So if we can like perform this query like very easily. So first we just initialize the entire array. So we start with an empty persistent segment tree, but we just continuously update the same root because we don't need like a partial segment tree. We just want the first array we want the first segment tree that corresponds to the entire array that's filled. So we just say update position I, and our segment tree goes from uh, 1 second. Oh yeah, this is supposed to be -1, but yeah. Yeah, so we want to update position I. The root node's range is 0 to n-1, and we want to update it with value A of I. And yeah, I messed up, yes. Oh no. I'll just say my queries on one index. Yeah. Yeah, so I update position I with value A of I, and I'm the node that I'm updating is roots of 0. So like I'm just updating the same node again and again and again. And now I'm going through the updates like from one to V. I want to update node X, position X with value Y. So roots I, which is like your new version of segment tree, it'll just perform that update where you do X0, supposed to be -1, but yeah, n-1, and update it with the value I, and you just take the previous version of the segment tree and yeah, just update it. And you just store that root in roots I. And now when you're trying to do the Q query, you just get LRV and you just plug it in. Just say that I want to query L to R, and the initial node range is 0 to n-1, and I want to query roots V version. So again, this is very simple. You're not going to get a question like this, but it's just to show how the segment tree can be used. So I hope that's clear. Any questions? Now, yeah. So I just wanted to ask you guys, do you guys know how to find the distinct values in a range offline using segment tree? Anyone who does it? Okay, cool. I'll just go over that then. Cool. Yeah. So finding this is like a very common like sub like subtask or like sub query that you have to do in a lot of problems where you have to like randomly query some range LR. Like there are many queries like this, and you need to know how many distinct values are there in that range. So if you're doing this offline, it's actually like a pretty classic problem, and I'll just go over that implementation. But uh, the use of persistence is that instead of doing it offline, you can do it online as well, which is required in some questions too. So um, the idea of solving this offline is that you're going to have many queries of the form LR, right? So LI, RI. So what you want to do is that you want to create a set like this. You're going to sort all the queries by RI, and for a fixed RI, you can maintain a segment tree such that it solves. You can manage all the queries which have uh, RI equal to that index. So to do this, I'll just try to come up with an example. So if you have the array 2, 3, 2, 4, 4, 2. Yeah, so say we have this array, and we're trying to solve queries of the form. Okay, okay, we'll go over the queries later, but we'll just go over the construction of the segment tree and see how we can solve this offline. So first we start off from index 0. Okay, I'll just use 0 index into it for this one. So these are the indexes, and we have and we have a segment tree on this other array that we made for this. 1, 2, 3, 4, 5, 6. Yeah, so we initially have this array and it's just filled with zeros. And we'll be maintaining a segment tree on this. So what we want to do in this segment tree is keep track of the last occurrence of each value. So over here, like when we start off, again, 2 is the only, like it's the first element, there's no repetition. So what we do is we just mark that position with 1. Cool. And if there are any queries of the range something comma 1, we can just answer it with this. Again, it's not going to be very clear, but I'll go a few steps in. So yeah. 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 So when we go on to position 1, you'll see that again 3 hasn't occurred yet. So we just mark that position as 1 as well. And now let's go on to position 2. So what we do is that we increment. Okay, I'm not going to draw the box in light. Yeah, so we increment this position to be 1, but we see that there's already been an occurrence of 2 before, right, at position 0. So what we do is that we update that index again to be 0. And now when we're at 2, whenever we make a query of the form L and R, say we want to query 1 and 2, we'll get that, okay, there are 2 distinct values. But when we query 0 and 2, you'll see that this one is not counted because you're only keeping track of the latest occurrence. So I hope this is intuitive, like why are we keeping track of the latest occurrence? Because as like, you want to support queries of the form L, comma J. And uh, I'm not exactly sure how to explain it, but I just hope you guys got it. Clear? Anyone has doubt? Cool, yeah. Like, I'm not exactly sure how to explain this part, but yeah, I hope you guys got it. Yeah, I'm doing the range query from R. Yes. Yeah. Basically that. So if you have like a fixed R, you want to make sure that you have the last occurrence of it. So as you go further left, you're not going to count the duplicates that come afterwards that are further left. You just want to make sure you only account for the first update, the first value that happens or that occurs. So again, this is the offline approach of this, where you just sort the queries and just build a segment tree from 0 to n minus 1. Now, if you look at the persistent version of this to solve this online, it's very similar. Again, yeah. So again, like we saw, we're building the segment tree incrementally from 0 to n minus 1 in the offline version, right? In a persistent segment tree, we just want access to all of these versions. So, like uh, if we look at this, right, we we had some array like 2, 3, 2, 4, 4, something like this, right? And we had a state of the segment tree at this position, state of the segment tree at this position, here, here, etc., right? And the state of the segment tree over here would correspond to all of the queries that we want to make, which are of the form L to this index. So Um, yeah. So say that we were trying to like do this online, and we came across we came across a query that was of the form 1, 3. Then we know that we want third iteration of the segment tree, and just make a query on that. And again, like we have like the definition of persistence, we can store all of these versions. So we just like the definition of persistence, we need a different version of segment tree for each set of queries that have rj equal to I. And we could just use persistence to save each version and just query it whenever we need that ri. We need that ri. So again, this is just a simple implementation of it. We store what is the last occurrence of each value, and we just have n+1 roots to keep track of each position's segment tree version. So we're going over like 1 to n. Over here, we're using one index just for simplicity. So we see that roots I is equal to update I1. Oh, this is for the sheet. 1n. Yeah. So yeah, over here we just increment like setting the current position to 1, and if there's a previous occurrence of that value, then we just update that position to 0. And set our last occurrence of the current value to I. And now we have a segment tree version for each of these indices. So if you want to support queries of the form LR, all we just need to do is this. We want to query L to R. The current segment tree range is 1 to n, and we want to use the art segment tree version. So it's basically just offline. It's offline, but you have access to every segment tree at any point of time. That makes sense, hopefully. Any doubts? Cool. So yeah, this is a pretty simple application of persistent segment trees, and now we'll just go on to finding the kth minimum. So first we'll just look at the classic problem of finding the kth minimum in the array 1 to n. So again, there's a very simple solution to this where you just sort it and just answer them, but what if you don't sort it? So to do that, it would be like you would have the segment tree, and never mind. So what you do in this problem is that instead of creating segment tree on the array, you create a segment tree on the frequency array. So like if we have the original array, which says like 1, 1, 3, 5, 5, 2, 2, something like this. It's not sorted, and what we do is that we just create a frequency array of this. So 1, 2, 3, 4, 5. Yeah. So the frequency of 1 is 2, the frequency of 2 is 2, the frequency of 3 is 1, the frequency of 4 is 0, frequency of 5 is 2. So instead we'll have a segment tree which is on this frequency array, and what we'll just do is perform a descent on it. So we're at like the initial so we'll have a segment tree which just stores like the sum. So we'll have 4, this will be 1, this will be 2, this will be 0, this will be 2, this will be 5, this will be 7. Sorry for writing on the text, but hopefully you guys can see this. Is it clear now? I guess. Yeah. Cool. So we're at this node and say that we want to find what is the third smallest value. Oh, no, we'll find what's the fourth value. Yeah, fourth value. So we're at this position, we look at the left node and the right node, and we see that, okay, cool, there are 5 elements on the left of me, in my left child, and 2 elements on my right child. Therefore, I need to go into my left child to find the third value. So you go into this. And yeah, over here again, you see that, okay, cool. The value that I'm trying to find is less than equal to my left child, so I can go into this. And you see that over here, for this node's left child, the frequency in the left child is 2. So you're like, okay, cool, no, I don't want to go there. I'll go into my right child, and you end up at position 2. And you basically find out that, okay, cool, the third smallest element in the array is 2. So again, this is just what descent does. It's pretty standard, I believe. I hope you guys got it. Fine. Huh? Yeah, so it's a pretty classic problem, again, but this is for 1 to n. How do you solve this for finding the kth minimum in L and R online? So again, like we saw, you were able to descend pretty easily on a frequency array and get what was like the necessary value in log in time. So if we had a frequency array for the range L to R, it would make life a lot simpler. So we can do that actually. So we can make a bunch of frequency arrays like this, which corresponds to the frequency where f of I indicates the frequency array of prefix I. So again, like we covered this in precision, like the previous example, it's pretty easy to just make all n versions of these, like the first element, the first 2 elements, the first 3 elements. So we'll have access to like f of I for all i's less than equal to n, less than equal to 1. And if we wanted to find what is both the frequency array of some range L to R, it would basically just be f of R minus f of L minus 1, right? So if we have access to both of these nodes at the same time, we can just perform a descent using these 2 nodes, or like the difference between these 2 nodes, and go down accordingly. So if you just look at this code, it's going to be very similar to the previous code, but instead, we just need to keep in mind that our frequency array is not just one segment tree, it's the difference between 2 segment trees. So again, if L is equal to R, which means that we've reached the position that we need to, and just return that position. Otherwise, we look at what's the frequency, like what is the sum in my left child in ID1, which is going to be R, and we find out what is the frequency, like what is the sum in A2, which is the frequency count in L minus 1. And that difference is basically going to be the number of elements that are in that range of that node and that are between the indices L and R, like inclusive. So yeah, if A2 minus A1 is greater than or equal to val, that basically means that, yeah, we need to go into the left child because there are more than val values in the left child, and we need to descend into that. Otherwise, it's just going to be a sub-problem where we just say that, okay, cool, ignore my left child, we need to recurse on a new problem, which is val minus A2 minus A1. So I hope that's clear. Yeah, but Mercer tree is slower. But Mercer tree is slower. Nobody, fractional cascading is usually slower. You'll find out. No. You'll find out. What I? No. Go try. The new version I told you. Yeah, so yeah, most of the yeah, this one you can, right? Yeah. Yeah, I mean, if you look at this problem, you can't just do that, right? For this, like, you can't do with secondary exactly. You would have to do something like square root decomposition, I think, almost, because you don't have access to both like L and R like versions of the segment tree. So that's why you need offline. You need online. So okay, I'll show you the next one. Yeah. I mean, like, okay, so there is one problem, like, it was like a suffix array plus precision secondary thing, in which I needed to binary search and find out like the number of distinct values in some range. And again, I won't know all of the queries I'm going to make, right? Because it's binary search. Like, I might go there, I might go here. So for that, I needed a precision secondary. So in that case, I actually need online, even though the question did not explicitly define online. So there are some problems in which you end up needing to do online. But yeah, so I hope this is clear. And yeah, so we're able to find the case minimum in the subarray L2R. And we'll just use this idea and generalize it to a tree. So extending this idea to the case minimum on a path. So to find, like, it's almost the same idea. So if you have some tree like this, and say we want to find out what is the what is the number of distinct sorry, what is the case minimum on the path from U to V? So on this path. So what you can do for this is that you store a precision segment tree for each node, and what that precision segment tree will denote is the frequency array of from that node till the root. So say if it was like 1, 1, 2, 4, 4, something like this. Like, so this will just store 1, comma 0, 0, 0, 0. This will store 2, comma 0, 0, 0, 0. This will store 2, comma 1, like that, and it'll just basically store like the frequency array from that node till the root. And again, like we said in the case minimum problem for a subarray, we just want to find out what is the frequency array of that subarray, right? So over here, we're going to do the exact same thing. So um, I'll just erase this. Yeah. Yes. Okay, I'll just create another tree over here. Yeah. So if, say, I wanted to find the frequency array from U to V, so it would basically be these values. So to get that, it would basically be f of U. Again, f of U basically denotes the frequency array till that node. 1 second. F of U. This is f of V. And again, the nodes above the LCA will be counted twice. So we need to subtract them twice. So uh, instead, we just like do this, in which we subtract this once because this is counted twice, and we want to make sure that we count the LCA, so we just subtract f of the parent of it. So f of u plus f of v minus the LCA of f of LCA of uv minus the parent of it. So again, I'll just how do I undo? How do I undo? No, undo. Okay, never mind. Yeah. No, it's fine. Got it. Got it. Yeah. So again, like we saw from here, the things that are counted twice or like once, we'll just see this here. So this is counted once, this is counted once, this is counted twice, 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 once, and everything like that. So again, we want to make sure that We subtract these both twice, but only this one once. And again, this equation will just take care of that. So I hope that's clear. That's fine. That's fine. Cool. Yeah. So yeah. So a lot of the problems, like, what do you say? Uh, like a lot of the problems requiring frequency array and like deltas across that, most of them are solvable by precision secondaries, or like you should just like try using them once in a while. Huh? Offline. Okay. Yeah. Um, oh, it's only been an hour. It's only been an hour. I'm pretty much done. Cool. Um, uh, this one. This one you can't. I'll show you this later, but yeah. Um, yeah. So now we'll go on to the concept of dynamic secondaries. So you guys might have heard of this or not, but I'll just go over it quickly. So a lot of like, not a lot of the times, but there are some questions in which you cannot actually quarter compress the values. So you actually have to work with values from 1 to 29, and you want to use a secondary on it. So in such a case, you you need to use a dynamic segmentary, and that's basically like the segmentary in which you don't create all of the nodes at the start. You just create it on the fly. So if you're gonna need ranges four to five, you create like you go down on the segmentary and you create the nodes then. And like for the rest of the nodes, you just leave them uninitialized so that you save on space. So that's why it ends up being q log n, because uh, for each query, you're going to update at max like log 29 queries, log 29 nodes. So yeah, and it ends up saving a lot of space, but it's slightly slower because the log factor is slightly larger. But if you look at how we've used persistent secondaries from the start, they have been empty from the start as well. All of them are initialized to be pointing to the secondary node 0. So persistent secondaries are implicitly dynamic secondaries as well. And if you look at, what do you say? Yeah, over here. If you wanted to support persistent segmentary of size 29, all you need to do is just make this 18 into a 30 so that you have the right log. And whenever you're making a, instead of doing like 1 to 25 as your root node range, you can just say it's 1 to 29 and it'll just work off. So persistent secondaries are very easily like you can modify them into dynamic secondaries, or you can just use them along with like precisions as well. So that is like one really useful aspect about precision secondaries. And if you just want a dynamic secondary, you can just change like one or two lines here and there and get a normal dynamic secondary as well. Yeah. Yeah, I mean, I know, technically the proposition. No, even if you do the pointer, it would still be something like that, I guess. Yeah, so there might be problems in which you require both. Again, not a lot of them, but sometimes you do. Like I've come across problems like that as well. And there's one more idea, which again, it's not a very like direct application of precision segmentaries, but it's a bit of an idea of like almost segmentaries in general also. But it's pretty useful. I've come across problems where you need to use them. But like, yeah, let's just go across like one type of problem that might require it. So say we need to compare two prefixes of two different arrays and across versions. Like we want to compare what is the frequency array of array A after the bth update, array A like up to L after the bth update, and array B after the R like up to prefix R and after the youth update. And like our form comparison is basically saying that we want to find the first element. or like the smallest number such that it occurs a different number of times in each array. So if the number 3 occurs 5 times in A and 4 times in B, we want to output that if 1 and 2 have an equal number of occurrences. So if we just try to do it with like a normal descent, that's not going to work because there might be like an imbalance in the what do you say frequencies, and you might just end up thinking that they're equal, but they're not. So if you had a frequency array like like one occurs one time and two occurs two times, and you had a frequency array of B in which one occurs two times and two occurs one time, and you look at the parent node of it, it's just going to be three, right? So there's no way to differentiate normally when you're trying to do a descent on these trees. So instead of just storing the sum of like your subtree, what you want to do instead is store some type of a hash. So again, 1, 2 would be different from 2, 1 in the hash. Like if you do like a normal polynomial hash, I hope you guys know hashing, but yeah, it's not that hard to see. So what you would do is that every time you update like a certain node, like say this becomes 3, what you do is that you have a certain hash for this, and when you go up, uh, you're gonna you're gonna want to combine the hashes of this in some way that you define, most likely a polynomial hash, and store a new value for this. So now, instead of just storing uh, the frequency of that range, you're going to be storing a hash of it, so that you know the first position at which the two ranges actually differ. So, what to say? Yeah. So if you had like two arrays in which I'll just draw one here for now, but yeah, and 1, 2, 3, 4, 6. Yeah. So you have this, you have this. So you just have this segment tree, and you have another segment tree that's equal. Just assume that there's one segment tree here. So So you just come in this position, and you look at the left child of this segment tree. You look at the left child of this segment tree. You're like, okay, cool. The hashes are equal. So now you know that the first position at which the frequency arrays differ is going to be in your right child. So you both descend into your right child, and then you compare again. Like, okay, maybe the left child is different here. So you go into this child, and then you basically descend down until you find the first position at which the hashes don't match, and like, saves this position. So then you know that, okay, cool. 0, 1, 2, 3, 4, 5. Yeah. So the number 5 has occurred a different number of times in each of the arrays. So yeah, using using hashing, you can actually solve like a lot more problems in which you want to find out what is the first point of difference between two segment trees. And uh, again, it's not a very standard like method that you use a precision segment trees, but it might end up helping you like solve problems in like a very different way, or like in an unintended way. So yeah, uh, polynomial hashing is what's usually used in such cases, but there are cases in which you want to use XOR hashing because it just simplifies your implementation a lot more. I won't be going much into it, but it's something that we might go on a different week. Yeah, and yeah, so this is a pretty short week. I mean, if you guys have any doubts, you guys can ask them, but I'll just go to the conclusion right now. So most, if not all, the segment tree techniques that we use, which is like data propagation, descent, or any other thing, if you can do it on a segment tree, you can most likely do it on a persistent segment tree. I've implemented a dynamic, persistent, lazy segment tree problem. It was absolute hell, but it's possible. So it's not absolute hell, but yeah, it is a bit of a pain. Yeah? Huh? Yeah, so if you want to implement a lazy precision segment tree, instead of just storing one integer for a segment tree, you can just store like a pair of events in which the first value indicates the segment tree node and the second one is basically your lazy array. And yeah, it requires a bit of practice, but if you just have your lazy implementation side by side, you'll be able it won't require a lot of practice to just map it one to one onto the persistent segment tree. So yeah, it's very powerful, and if you need anything offline, persistent segment trees is your best bet, and you can just use it. Huh? Oh, online. Sorry, online. Yeah. And yeah, so right now I just covered segment trees and like making them persistent, but Again, this idea is very generalizable. There are a lot of data structures which can also be made persistent. There are persistent trees problems. There are persistent centroid tree problems. You can make tries persistent as well. So there are a lot of ideas, and like good way of just understanding if a data structure can be persistent is, uh, are there a lot of things that you update when you're making a lot of nodes, or a lot of things that you update when you're making an update? And if not, like if it's like around login or root or something like that, you can just try to make a persistent version of it by just looking at the ideas of a persistent segment tree and try to generalize it onto your new data structure. And yeah, so there are a lot of techniques that are involved in persistent data structures, and a lot more that you can come up with. Again, so this is one idea that I came up with when I was implementing like a certain problem, and you'll come across a lot of problems which will help you invent new techniques with persistent data structures as well. So that's pretty much it. These are just a few guides that I've used before in the past, and hopefully a features to come out in the next few days that will be like a good set of persistent segmentary problems, and it'll have a good range of them as well. Yeah. And that's pretty much it. Any questions? Cool. I'll end the meet. Cool. Thank you all for joining, and I'll just end the meeting.